In this talk, I will describe my work on active sensing in the categorization of visual patterns. This work is done jointly with Mate Lengel and Daniel Wolpert at the University of Cambridge. Categorization of visual patterns is often time-constrained and difficult in natural scenarios. Imagine that you are in the wild, and you see a patch of fur hidden behind some foliage. You want to quickly figure out whether the fur belongs to a zebra or a cheetah, so you can take the necessary action. And due to the limited acuity of our peripheral vision, we need to direct our foveal vision to scan the scene, make multiple fixations at different locations, and integrate the information across these locations in order to solve the task. Now I'll show you the answer. Thus, our categorization performance depends crucially on the particular sequence of eye movements we make. A passive, predetermined scan path is not optimal, as the optimal next eye movement should depend on what has been observed about the actual scene and should hence be active. The optimal eye movements can be formulated as a Bayesian active sensor. The sensor uses two sources of knowledge. The first is the prior of the statistics of different visual patterns. The second is the evidence accumulated about the actual scene from previous saccades. Using this knowledge, the sensor first computes the probability that the scene belongs to a certain category given the evidence. In this example, whether the observed fur belongs to a cheetah or a zebra. Then it computes where to look next so as to maximally reduce categorization error. Previous works have mostly studied active sensing where the latent feature of interest is only spatial. Examples include, firstly, simple visual search tasks, secondly, object localization tasks, and thirdly, shape memorization tasks. Other works have studied active sensing where the task allowed only one fixation. Examples include searching for a hidden target or face recognition. We want to study active sensing in more natural tasks. Motivated by Yarbus, who examined eye movement in tasks such as the one shown here, where the participants need to look at the image and estimate how long has the visitor been away from the family. We want our approach to include several properties of such natural tasks. First, the task requires abstract information. Then, any single location is insufficient in information to solve the task, and information must be integrated across multiple fixations in the scene. Foveal vision is often more important than peripheral vision in such cases. To keep the task natural yet mathematically tractable, our approach to include these properties is to construct simple stimuli and use a gaze contingent display to control the information participants can get with each fixation. This allowed us for the first time to find the fixation by fixation efficiency of each eye movement and allowed quantitative comparison to the optimal active sensor. For our experiment, we constructed two categories of visual patterns, a patchy category and a stripy category. The stripy category contains two patterns, horizontal stripy and vertical stripy. The reason for having two types of stripy pattern is that with only one type of stripe, always scanning along one direction will be optimal, and that strategy can be predetermined passively, independent of the actual image. These patterns are constructed using two-dimensional Gaussian processes with different horizontal and vertical length scales for each of the three patterns. This allowed us to generate infinitely many examples of the same pattern. Some of them are shown here, without any of them being the same. Furthermore, due to the probabilistic nature of the process, no single pixel is informative enough, and the category information increases gradually as you get more and more pixel values at different locations. The experiment consists of 3 phases. In the first phase, the training phase, participants were shown the entire image. Upon choosing a category, an audio feedback on correctness was given. In this phase, we familiarized the participants with the statistics of the patterns. Participants' performance was perfect when shown the whole image. In the second phase, the active revealing phase, the image was entirely masked. The participant can freely scan the scene, and we use a gaze contingent display so that wherever they fixate, we reveal a small aperture of the underlying image. The participants were instructed to keep looking and revealing until the category choices appear. Upon making a choice, they were then shown both the underlying image and the audio uncorrectness as feedback. The number of revealings allowed was chosen randomly from 5 to 25 in intervals of 5. This random stopping criteria was unknown to the participants and encouraged them to be greedy in their information seeking. In the third phase, the passive revealing phase, everything was the same as the active revealing phase, except that the revealing locations were controlled by the computer, and the participants were instructed to just follow the revealings as they appear one by one. These locations were chosen according to several different algorithms. I will talk about them when we get to them later in the results section. We note here that the participants completed all active revealing trials before entering the passive revealing phase. These ensured that their scan paths were not influenced by other revealing strategies. Now I will give a general overview of the model. We start with the first probed location x1 and the perceived pixel value z1 there. Let's say we have observed n of these position pixel pairs in a trial until now. We call these data D, the observations. Through an ideal observer model, we can infer the category given these observations and also predict possible perceived pixel values at potential probe locations. These locations then feed into the Bayesian active sensing algorithm, which selects the next probe location, from which we will get another perceived pixel value. To compare this closed loop model to our participants, we added 2 realistic constraints to our ideal observer model. The first one is perception noise, that says the perceived pixel value is corrupted, a corrupted version of the displayed value. The second is a representation bias that says the length scale of the patterns may not be represented ideally. We also know that humans have noise in their motor system. That is, even though they planned to look somewhere, they will end up looking somewhere else. This is particularly true in our active revealing conditions, where saccades were usually made to a place without a visual target. Now I will go through in more detail what this Bayesian active sensing algorithm is. The Bayesian active sensing algorithm, which we named BAS, aims to choose the next revealing location that will improve categorization performance the most. Let's say we have some observations and have computed the posterior probability. Then for any potential probe location x star, we can compute the distribution of the possible perceived pixel value z star at x star. Here the word possible is used because we have not observed that pixel yet. Given a particular pair of possible probe location and perceived pixel value, we find a possible update of the category posterior. we work with the entropy of the posteriors. The H denotes the entropy and corresponds to uncertainty. So if you are certain about the category, the entropy of the posterior will be low. And if you are uncertain, the entropy will be high. We compute the entropy of category posterior before the update and after the update. But because we have not yet probed X star, and therefore do not know the actual pixel value there, we have to average the updated entropy over the distribution of possible perceived pixel values. We define a score as the difference of these two entropies. The score is then the expected reduction in uncertainty in units of bits about the visual categories if location X star is probed. And the Bayesian active sensing algorithm chooses to probe the location with the highest score. This score is the well-known expected information gain. Note that it is also the mutual information between the category C and the pixel value Z star. This means that we can swap C and Z and write the score in another form. Now, with the probability being in pixel space, it gives another perspective on what the algorithm is doing. The first term shows that the algorithm wants to go for a location where the pixel value is overall uncertain. But this is modulated by the second term, which favors locations where the predicted pixel value given a category is certain. Now we show the fixation locations generated by the BAS algorithm without motor noise added, which we also call noiseless BAS. We start with a vertical stripy underlying image. The algorithm, of course, does not know that. Having fixated the center, the algorithm computes a grid of scores and goes for the locations with the highest score. And this procedure goes on. We now come to the results. We first address the question of whether our participants were active in their sensing, that is, whether their choices of revealing locations depended on what they observed about the image. To do this, we look at the density of revealing locations. Shown here is the normalized density map of revealing locations pooled across all trials in the active revealing phase for participant 1. For each of the 3 patterns, we compute the normalized density from trials that use that pattern of underlying images and subtracted the mean from it. Then we obtain these difference maps. We do that for all 3 participants and their average. On this map, red means that the participants tend to fixate more at those locations, while blue means less. For example, with a vertical stripy underlying image, our participants tend to fixate more along the vertical axis and less along the horizontal. The point is this: the fact that these difference maps are distinct for different underlying image patterns means that our participants were active, as the underlying image was unknown to them before they observed anything. To quantify this, we compute the correlation among difference maps. The correlation is computed in the following way. We computed the correlation using many random splits of the revealing conditions. For a within pattern condition, we see a positive correlation. And then for a cross pattern condition, we see a negative correlation. So this confirms quantitatively that difference maps are distinct, and thus our participants were active. Next, we ask whether the participants' active sensing strategy helped their categorization performance. Here we look at the fraction of correct category choice as a function of revealing numbers allowed. First, we see that participants did better when they actively chose the revealings themselves, compared to when we show them revealings randomly sampled from an isotropic Gaussian distribution centered on the scene. However, when we show them the revealings generated from the noiseless pass, which is the algorithm shown without adding in the motor noise, they actually performed better. This seems to suggest that although the participants were active, they were quite suboptimal. So we asked, what could have given rise to this gap, and what is the efficiency of participants' sensing strategy? To address this problem, we looked at the information gain with each revealing according to the observer model described previously. The two parameters of the observer model is perception noise and representation bias, and they are specified through fitting to the participants' category choices. The fit results are shown here. Using the observer model, we can compute the cumulative information gain in bits as a function of revealing number. Information here is defined as 1 minus the category entropy in bits. So when nothing is observed, we would expect total uncertainty about the category, which means an entropy of 1 bit and a cumulative information of 0 bit. As the observer gathers more data, the entropy decreases and information about the category increases. The information gain plots recapitulate the top plot, that the participants' active sensing strategy was more efficient than the random strategy at gaining information, but less efficient compared to the noiseless patient active sensor. Now, as mentioned before, humans have noise in their motor system, and even though they wanted to look somewhere, they will end up looking somewhere else. We measured this motor noise in a separate experiment where we asked the participants to saccade to a remembered target location without seeing the target. When we added the measured motor noise, we see that this closed more than half of the gap, showing that after accounting for this realistic constraint, humans are actually quite efficient. Comparing the green and the red curves, we quantified that the central process of selecting fixation locations is about 70% efficient. Furthermore, we ran this Bayesian active sensing algorithm with the same images and revealing numbers used by the participants and obtained these density maps. As you can see, the density maps generated by BAS closely resemble those of the average participant. Quantitatively, we confirm this match by showing that the within pattern correlation is significantly positive and that the across pattern correlation is significantly negative. Lastly, we want to test whether simple heuristics that depend on biases in fixation locations can account for our participants' eye movements. For the first heuristic, we considered a feed-forward strategy that does not depend on observations. Each new fixation is then obtained by sampling from the participants' fixation densities. Here we split the average fixation densities according to the order of revealings, that is, into 25 maps. Then the ith revealing of the heuristic is sampled from the ith map. We call this heuristic the order-dependent fixations. It emulates a sensor who does not use the information of the observations, but depends solely on some order-specific average bias in fixation locations. The second heuristic uses the observations. It first computes the type posterior given the observations. Then it finds the type with the maximum posterior. Then it samples from the fixations that have that type as the underlying image pattern. This is done independent of the order of revealing numbers, so we call this heuristic the posterior dependent fixations. The final heuristic is called the posterior and order dependent fixations. And as the name suggests, it samples from the fixations in both a type-dependent and order-specific way. We simulated these heuristics, obtained the revealing locations, and computed the corresponding information gain curves. The results are shown here. The three heuristics turn out to perform very similarly. Importantly, all three are less efficient than the locations chosen by the participants. This result further supports the idea that a closed-loop Bayesian interaction between observations, belief update, and eye movement selection is what underlies our participants' eye movements. In summary, we designed a task where integration of visual information into abstract categories is necessary. Our results show evidence that humans are about 70% efficient in their fixation by fixation movement planning, and that a large fraction of inefficiency is due to perceptual noise, representation bias, and saccadic variability. Lastly, I would like to thank Mate Langell and Daniel Wolpert, who worked on this project together with me, and James Ingram for helping the technical details of the experimental setup.